I'm not even sharing all my things. That's right, we did stereochemistry. What is stereochemistry? Isomers? Tell me more. Not you necessarily, anyone can tell me more. The arrangements of atoms in space. So isomers can be two major types of isomers. What are the two major types? Constitutional and stereoisomers. And what's the difference between constitutional and stereoisomers? That's a little too specific on the stereoisomers. You're getting down into the next level. Zoom out a little bit. Let's try again on defining the difference between constitutional and stereoisomers. Yes, so constitutional isomers deals with like if it's got a different condensed formula, it's like constructed differently, the structure itself is different. And then stereoisomers is when it's arranged differently in space. So we have isomers, and we broke our isomers down into constitutional. And my favorite example for this is if you have pentane versus, I think this is tert-butane, but 1,2,3,2,2 dimethyl propane. These are both made up of 5 carbons and 12 hydrogens, but they're arranged differently in space. And then there's stereoisomers. And stereoisomers are when things are arranged differently, like they have the same condensed formula, but they're arranged differently in space. So a good example of this is 2-butanol. If you had 2-butanol, it could be one of two either mirror images, or if you have, it needs to be either R or S. And then if you have cis or trans of something. So like if you had 1,2-dichloroethane, sorry, there should be a dash there, 1,2-dichloroethane, it could either be cis or trans, so you have to specify. And then 2-butanol looks like this, so there is a stereo center right here, so you need to make that either a wedge or a dash. Okay, awesome. Now, how do we break stereochemistry down even more? Close. Chiral and achiral. That's a type of stereoisomer enantiomers. Enantiomers are chiral molecules. And what does chiral molecule mean? A mirror image that does what? Non-superimposable, or sometimes called non-superimposable. So enantiomers are mirror images, not superimposable. And then what's on the other side? Diastereomers. What are diastereomers? I heard a lot of definitions I like. Not mirror images. That's true. It still has to have the property of being a stereoisomer, but if it's not a non-superimposable mirror image, that is a diastereomer. Oh, I didn't write it. And I heard someone else say everything else, so that's what I usually say. Everything else. My handwriting's terrible. Okay, so those are kind of our big picture ideas. Did I forget anything? Oh, we also learned something else yesterday. Something big. RNS configuration. What is RNS configuration? Well, I'll start with where do you use it? On enantiomers or diastereomers? So far, we've only used it on enantiomers, although sometimes you can use it on diastereomers. So far, we haven't. Okay, RNS configuration, and what are they? How do you find them? Label the priority, and what do you label the priority based on? Atomic weight or mass, whatever you want to say. And is it the atomic mass of the whole group or just one thing? Atomic weight of directly attached atom. And what happens if two are the same? If two are exactly the same all the way down, it's not chiral. If two are exactly same at the first point of attachment and you keep going and at some point there's a difference, you got to keep going down the line. Then once you find the first point of difference, that's what you use to decide. So both of you said two different things and both of you are right. Okay, and then what do you do last after you've assigned the priority and the atomic weight? I don't know why I put this as two. Yes, lowest priority molecule in the back. Perfect. And in my office hours today, we had a lot of conversations about different ways that you can do that. So you can either break bonds and flip it and know that that's the opposite of your actual configuration, or you can rotate the whole molecule. And we worked some with Fisher projections and saw that there are a lot of different ways you can accomplish this goal. My advice to you is to find a system that works consistently before the exam. Implement that system, make sure you're consistently getting the right answer and use that. Also remember, you can use a modeling kit on your exam and your quizzes from now on. You can always use a modeling kit. Okay. And then what do you do last? After your lowest priority molecules in the back. You connect 1, 2, and 3 and check if there are, this is clockwise, so that's R. This is counterclockwise, so that's S. Okay, and then when you're actually doing the nomenclature, it's usually before, and then it'd be like S, butan 2-all, for example. Okay. Yes, thank you for asking. If the hydrogen is pointing directly towards you, was the question, will that reverse it? So let's do a quick practice problem. This was from your exam, or from your quiz, I mean. Okay, so there are a few ways you could do this problem. One way, you can rotate the whole molecule. So you would have to rotate literally the whole molecule. So this is pointing up now. We're flipping the whole thing. And initially, I'm gonna face your way. So initially this hydrogen is pointing towards me, right? My thumb's the hydrogen. And this kind of mimics the wedges going towards you and back, and this is the plane of the page, right? So the hydrogen is pointing towards me. If I rotate this whole molecule, what happens to the hydrogen? Now the hydrogen's pointing back. So when I flip this whole molecule, the OH starts to point up, and the hydrogen goes to the back, and the iodine goes to the front. Another way you could do this, if it's easier for you to visualize, the hydrogen's pointing towards you, you can just imagine if I was looking at it from the back side of the molecule. Either way, that's fine. Okay. So I rotated this whole molecule. Hopefully I did that right. I'm pretty bad at rotating molecules. What's the highest priority? And then what's the lowest? Hydrogen, that's why we made it point back. And then these two are both carbons. What are they each attached to? What's this one attached to? Oxygen, and what else? 2 hydrogens. And what's this one attached to? Carbon and 2 hydrogens. So this one wins. So 2, 3. 1, 2, 3. So that should be S configuration. Okay. Another way you can do it, I'm going to put it in a different color so you know that this is like a different method, is you can just pretend that that hydrogen isn't there. And luckily we've already done our priorities. 1, what's 2, 3? 1, 2, 3. That's pointing to the right, that's clockwise, but your hydrogen's pointing directly towards you. So I know that that's wrong and it must be the opposite. So S. Okay, a third way you can do it is if you break the bonds and reattach them so it's easier for you to visualize. If we did this, we know that this is the opposite. This is the Alice in Wonderland, opposite world. Is that what it's called? Sheila, I think you gave me that. What's Alice in Wonderland opposite world called? Yeah, In the Looking Glass. Is that what it's called? Okay, we're in the Looking Glass. In the Looking Glass. I've never seen that movie. I really should. My mom's name was Alice. Okay. In the Looking Glass. So in the Looking Glass, we have 1, 2, 3. And that's R. And now we're going to leave the Looking Glass and it's S. So all 3 of these are possible ways that you could assign RS configuration to this same molecule. Okay. Did that track? Did that answer your question? Yes. No, I just put a number on this whole side, right? Like, so this side is 2 because of the alcohol, but I don't actually have to number the alcohol itself. I just have to know that this side is 2 and this side is 3 and this is this. It's only 1 atom, so that 1 is 1. Yes. Oh no, that's a great question. Again, I'm bad at rotating molecules, so I don't do this, but you can do this. You can rotate it around this axis, not the mirror image, because what's the mirror image? The mirror image is the enantiomer. So you have to actually rotate it around this axis. So rotating it around this axis would make the alcohol go to this side. The iodine comes forward. And the hydrogen goes back. And then that's the same. Okay, so I am going to show you the mirror image so you can see the difference. If I took the mirror image of this, it would look like the hydrogen still being pointed forward. So see the, nope, I drew that backwards. That's a hydrogen. That's an iodine. So this is the mirror image. Do you see how that's the mirror image? And do you see how this whole molecule was flipped? It's all about the hydrogen and iodine wedge and dash. So if it starts with the hydrogen pointing towards you, and I rotate the whole molecule, now the iodine is pointing towards you and the hydrogen is pointing away. But you also had to move the alcohol and the group on the other side. So you move the whole thing. Or you can move it like this, you know, or you can just swap those 2 only and know that you're in the Looking Glass, which I'm obsessed with. Okay. Does that answer your question? Okay, we're gonna have a lot of time, hopefully. We spent a lot of time chatting this morning. We're gonna have a lot of time in our recitation. I'm aiming for, who knows if this will happen, the full second half of class that you get to work on your recitation, but like maybe not because we chatted about the exam and quiz and stuff, but I would like, and I think that's valuable too, but I would really like for you to have ample time to work on your recitation today because I do think practice problems are valuable for this type of thing. Okay, so with that in mind, let's dive in to where we were, which was right here. Okay, so up to this point, we've only seen R and S configuration used on like 1 stereocenter, 1 chiral center, and if you have the mirror image of something with 1 chiral center, it's going to be its enantiomer. But I very briefly introduced to you the idea that sometimes you can have 2 chiral centers. And then I posted a video, which all of you watched immediately, I'm sure. And there was something else called a meso compound on there. And that's a fun complication of us having 2 stereocenters. We can have diastereomers with chiral centers, which is new. We can have meso compounds, which mess everything up. And then we can still just have regular old enantiomers. So we have to consider the number of chiral centers as we go kind of through this. So, and we briefly talked about how in compounds with however many chiral centers, in this case 2, the possible number of stereocenters is 2 to the n. So 2 squared would be 4 in this case. So I'm going to show you because I think it's way easier to see on the visualizer. But I'm actually going to swap 2 of these out so that we don't have meso compounds because they mess everything up. My husband always gets mad at me for leaving lids off markers too long. It's, you know, it's a product of ADHD. What can you do? Okay, and then this goes here. Okay, so would you agree that this has 2 chiral centers? Yeah, I think so too. Now, is this the mirror image of that molecule? No, it's the mirror image if you only looked at the top half. Do you see that? But the bottom half, what is it? It's identical. So let's randomly say, I'm not going to actually assign priority, but let's say this is R. And let's say, let's also say this is R. So we have the mirror image of the top one, so it becomes S, but the bottom one is the same. So if we were to assign the priority, I hate how this is like not able to focus on my hand. So if we're able to assign the priority and we don't have the mirror image, it's the same, so this would still be R, right? Okay, so far we have RR as one stereoisomer, and now we also have SR, RR, and SR. Okay, now I'm going to take the mirror image of RR, and what do you think the mirror image of RR, what do you think that stereochemistry will be? What do you think the assignment configuration would be? SS, that's right. So that's another possible thing that we have. This is the mirror image of that original one. So RR, the mirror image of that is SS. Okay, and now what if we took the mirror image of SR? So this is S. Let's make it R. No, this is RR. This is RR, and this is SS. Okay, so let's take the mirror image of this one. So this becomes R. And the bottom one stays S. So that is, here we go. These are mirror images. So now we have SR and RS. Okay, so these are the 4 possible, 2 to the N with 2 chiral centers is 4. So these are the 4 possible stereoisomers you could get. RR, SS, RS, and SR. Now, I showed you originally RR and SR, and I said these are not mirror images, right? And you guys all agree? What do you think the relationship between those 2 are if they're not enantiomers? Diastereomers, because diastereomers are everything else. So if you have a molecule with 2 chiral centers and one is kept the same and one is changed, it's not mirror images, but it's still a stereoisomer. The condensed formula of this would still be the same, right? It'd be like CH3, CBRH, CCLH, CH3 for both of them. But they're also not mirror images. So the only thing left is diastereomers. They're also not cis-trans because they can rotate around a single bond. So the only thing left is diastereomers. Okay, I think it's easier to visualize that with the actual modeling kit, but this is showing you the same thing. So here's the mirror image of the top one. These are enantiomers, but the top molecule here is kept the same, and the one with alcohol and CH3 is swapped on the bottom. So that makes the relationship between 1 and 3. That's right. Okay. And so 1 and 2 are enantiomers, 3 and 4 are enantiomers, and then everything else are diastereomers of each other. So 1 and 3 are diastereomers, 1 and 4 are diastereomers, 2 and 3 are diastereomers, 4, yeah, this way and this way are diastereomers. And this way. Okay. Okay. Now let's talk about how to tell if something is chiral or achiral. And I know a lot of you saw this already. This is where meso compounds come in and mess everything up. I know a lot of you saw this already in your homework questions. So we talked about a few different definitions of chirality, and one of them had to do with the plane of symmetry. Do you remember what that one was? Does a chiral molecule have a plane of symmetry, or does it not have a plane of symmetry? Does not have a plane of symmetry. A chiral molecule does not have a plane of symmetry. So, does this molecule have two chiral centers? It doesn't? How many different groups are attached to this carbon right here? CH3, we'll call that bromine, hydrogen, and then this group. Are those all four different? Yeah, so is that a chiral center? Yeah. What about this one? Is this a chiral center? Yes. Two chiral centers. However, I think you guys all see what I see, which is why you said no initially. What is present here? There's a plane of symmetry. If you chopped this right down the middle and reflected it in a mirror, it would complete the molecule back the way it looked before. These reflect over each other to look the same, these look the same, and these look the same. So when that happens, though there are two chiral centers and there's four possible stereoisomers, you actually only have three stereoisomers because of the plane of symmetry. Because if you reflected this, there we go. Because if you reflected this and got the mirror image, you agree that this is the mirror image, it is superimposable. So even though there are two chiral centers, am I recording? Okay, good. Even though there are two chiral centers, are these two stereoisomers? No, these are identical. This is not a chiral molecule. The mirror image is exactly the same as the original molecule. So that gets rid of two of our possible stereoisomers. So one thing I kind of want to show you is which two it gets rid of. If this is R and this is a mirror image of R, what do you think that would be? What configuration would that be? If this is R and it has a mirror image of itself, what is this? S. That's right. So meso compounds are either RS or RR configuration. These two are the same. There's only one molecule because they have to reflect themselves in the mirror. Okay, so these two are the same. That's the one that we get rid of because it has to be reflective of itself. So when I'm looking to see if something is, yes.
Is it possible for molecules to have a chiral center with the entire thing?
That's what this is. It has two chiral centers, but the entire thing is not chiral. But if it has one chiral center, that's not possible because inherently one chiral center means that there is not a plane of symmetry there. But if there's two chiral centers, the plane of symmetry can happen between the chiral centers. Good question. Oh, what was I saying? My Adderall is wearing off. What was I just talking about? Does anyone remember? Meso compounds in general, but this specifically, I was going to make a point. Yeah. Oh, I know what I was going to say. Thank you for that. Okay, so when I'm looking to see if something is a meso compound, the things I look for are the things attached to chiral center 1 and chiral center 2 the same? So you can see here, chiral center 1 has a hydrogen, some kind of halide, we'll just call it fluorine, whatever, and carbon. So does carbon 2, or chiral center 2. So both chiral centers have a hydrogen, they have a fluorine, and they have a CH3 group, right? Same thing here. So if you have to have all three things the same in order for that plane of symmetry to exist. If we swapped one out, immediately the plane of symmetry is gone. So that's the first thing I look for. Well, I look for two chiral centers, and then I look to make sure both chiral centers have the same things attached to them. And then I try to find a plane of symmetry. Because if there's not a plane of symmetry, even though this molecule has three things attached to it, same three things attached, there's no plane of symmetry here, right? So if I take the mirror image of this molecule, how did I get that? I take the mirror image of this, it's not superimposable. So it needs to have two chiral centers to be a meso compound. The two chiral centers need to have the same things attached to it, and there needs to be a plane of symmetry down the middle. And a way you can check to make sure there's a plane of symmetry down the middle is you can assign R and S configuration, and if one is R and the other one's S, then they are reflecting each other. You can visually rotate the molecule to see if the plane of symmetry exists, or I would say those are the two big ones. Either you can rotate it or you can assign R and S configuration. Yes.
The two chiral centers that the meso compounds must have to be connected to carbon. Okay,
Usually chiral centers are carbon and ochem.
but I mean, it's attached to another.
No, it could be. Did I say that attached to another carbon?
I don't, they interpret it that way, I don't know, that's.
Okay, it's possible that I said that. No, you could get rid of this CH3 group and it'd be like, we'll pretend this is a iodine and that's a fluorine or whatever we said earlier. Oh, I don't have 4 of these blue ones. It doesn't have to be carbon. Any group that's the same on both of them, it just has to be the same on both of them. So if you had this, thanks for your patience. And let's swap this one out. I stole my boss's modeling kit because hers has more colors for this exact reason. I guess she's not technically my boss anymore now that I'm graduated. That's kind of sad. Okay. Oh wait, we're proving that it doesn't need carbon, right? So if you didn't have carbon, so say this is a halogen, this is a different halogen, and then hydrogen, this still has a plane of symmetry down the middle. So it doesn't need 2 carbon chains to be a meso compound. So this one, it just has to have the same 3 things attached to that carbon. Maybe that's what I said. So it has to have the same 3 things attached to the chiral center, and chiral centers are usually carbons in ochem 1. So that's probably actually what I said. Yes.
If the 3 things connected to one carbon bond. Like instead of the 3 things, how should I do that? So all of them must be connected.
Do you mean, I'm going to give you a few options. Do you mean like this, where I swap 2 and there's not a plane of symmetry? Okay, you tell me, what's the relationship between these 2 molecules? Are they enantiomers? No, they're not mirror images, so they can't be enantiomers. So what else could they be? Diastereomers, that's the only thing left. So they have to be diastereomers. So if you swapped it like that, they would become diastereomers. Is this a chiral molecule? It is a chiral molecule because this does have a mirror image that's not superimposable, right? So this would be representative of the, you try to put those on the can. This would be representative of like RRSS. The plane of symmetry would be the one that's RS or SR. Yes. No, it's identical. So its mirror image is the same. So if it's like, what's the relationship between these 2? And it's a mirror, it's a meso compound, then you'd say, oh, the relationship between these 2 are identical. So that's a good question. So we call something, sorry, we call something a meso compound that has the property of, if you take the mirror image and it's the identical molecule, that's a meso compound. If it has 2 chiral centers, or usually I think it has to be, does it have to be an even number? Yeah, if it has an even number of chiral centers and the mirror image is the same, that's a meso compound. The property of having 2 or more chiral centers and the mirror image not being an enantiomer is a meso compound, but you would call the mirror image identical. I don't know why I just use my hands as if those aren't enantiomers. Yes. Say that again. If there's a meso compound, what? Yes. So like this is not a meso compound. These are not superimposable. These are enantiomers. This is a meso compound. So there's a plane of symmetry here. There's I know it's a meso compound because there's two chiral centers. And between those two chiral centers, there's a plane of symmetry. So now I can, just to prove it to all of us, make the mirror image, boop. And these are superimposable, so these are identical. These are the same molecule. There's not a left and right hand to this molecule. Its mirror image is the same as itself. It's not a chiral molecule. You're welcome. And I feel like sometimes when we get so in the weeds on these kinds of things, it's like, why do I even need to know that this exists? And you're like, bleh, I don't care. I totally get it. Sometimes I don't care either. And like, does it matter? But it does, because remember the stuff with thalidomide, we as people who work consistently with medicines or who develop medicines, etc., we need to know how is the handedness of this molecule going to impact us, or is there no handedness to this molecule, right? So it is important to know. It's important to be aware that this concept exists and to be able to talk about it, especially because you're going to get to biochem and you're going to talk about this even more with sugars. Because biochem is all about molecules that exist in real life, and molecules that exist in real life have handedness. So, okay. Let's go back to the slides and see what they tell us. 45. Okay. I don't know why this one already shows the RNF site. My animation on here is bad, but you can see that RR has does this have a plane of symmetry? No, the CH3 is pointing backwards. So these are RR and SS. But RF, there's a plane of symmetry right down the middle. The CH3s are both wedges, the hydrogens are both dashes, and the bromines are in the plane of the page. So what are these two molecules? It is a meso compound. What's the relationship between these two? Identical. So 1 and 2 are enantiomers of each other, and it's a chiral molecule. 1 is a chiral molecule, 2 is a chiral molecule. They're two different chiral molecules. They're enantiomers of each other. 3 and 4 are identical. This is an achiral molecule. It's just a different way of representing the same molecule. It's identical. Okay, so if you were to name this like a 2 chiral center molecule, you just look at one side and then the other, but the rules are basically the same. So here, the bromine would still be the highest priority. Then we compare these two carbons. So what is this carbon bonded to? Bromine, hydrogen, a carbon. What's this carbon bonded to? 3 hydrogens. So which one wins? 3 or 1? 3 is higher priority. So 1, 2, 3. And this is already pointing backwards, so we don't have to worry about it. So that should be an R configuration. Let's hope. Whenever I do these on the fly, I'm like, what if I'm wrong? I'm not. Phew. Okay, so we would assign that one, and then you would just assign the other one in the same way. So in this case, the bromine is pointing away from us. So what I'm going to do is I'm going to find the configuration and then invert it. So this is 1, this is 2, this is 3. We already decided. So this is S. So the inversion of that would be R. So is this a meso compound if you have 2 R configurations? No. What does a meso compound have to have? S and R, because it's reflecting itself across that middle plane. Okay, so this is showing you to number the other one. 1, 2, 3. They rotated it. I don't do that. So it's R. So the full name you would have in parentheses 2R, 3R. So the 2 and the 3 denote on which carbon in the parent chain it's in. And then R or S, obviously, you would assign that. And then the rest of the name would be the same. So on our, I think I showed this as an example when I did I already made the quiz video. I just haven't posted it yet. So on the quiz video, I named that butanol, 2-butanol thing that we have, the whatever, what was it? Oh no, 2-iota. So I did 2, I can't remember if it was R or S, I think it was S. 2S dash, 2S in parentheses, dash, 2-iota butan 1-ol. Right, so you can see me practice the nomenclature on the quiz just to take it one step further for you. Okay, and then also cyclic molecules can be chiral. I want to talk about Fisher projections. Let me see if they have it on here because I think it's important. It comes later. I'm gonna do it now before we get to rings. Okay, so a really great way to deal with things that have two chiral centers are using Fisher projections. Dr. Berhe doesn't require you to do these. Dr. Danikar does. I think they're really useful, so I use them. Okay, so we've been looking at these molecules like this a lot, right? This is eclipsed, as you can see. So a way that we commonly look at molecules to see the symmetry, because it's easier to see, is in this eclipsed form. So if I were to draw this, I'm going to put these as carbons again, because I think carbons are easier to draw. So if I were to draw this in the sawhorse notation, or the wedge dash notation, you'd have, what is this? What is the parent chain here? Parent chain is butane. And then let's say those are fluoros. So what position are those fluoros at? 2 and 3. Difluoro. So this molecule would be 2,3 difluorobutane. No space between. I just ran out of space on here. Okay. But that's not the full name because these could be arranged this way or this way or this way or that way. So we're going to figure out RNS configuration. So if I were to draw this in the bond line notation, normally we go up and down, right? When we go up and down, there's a wedge and a dash, a wedge and a dash. So if this is up and down, the hydrogen would be pointing towards me. This fluorine would be pointing away from me. Up and down. This fluorine would be pointing towards me, and this hydrogen would be pointing away from me. That's kind of hard to see the plane of symmetry that was once so obvious, right? So we actually don't tend to draw things with two stereo centers in the bond line formula because it's kind of hard to see the symmetry. So we draw them in a way that makes it easier for us to find that meso compound. So instead of drawing it like this, we sort of draw it like this, where there are 2 hydrogens pointing towards us and 2 fluorines pointing away from us. But still, that's kind of weird because if you're trying to rotate it or whatever, I don't know, it's just like kind of hard to get it to see if it's exactly right. Like what if you had it drawn like this and you needed to rotate to see if these were lined up? You have to be pretty good at rotating 3D structures. Yes. No, neither of these are cis or trans. They're just RS because there's not a double bond and it's not a ring. That's the only time you'll have cis and trans. Thank you for asking. And rotating does not change the conformation or the stereoisomer because they're not breaking bonds. So rotating doesn't change anything. But if it was cis trans, you would have to break a bond. Remember, I'd like pull that one off and put it back on and make your double bond happen. So if you were doing the same thing in cis trans, if there's a double bond, yes. But in a single bond, no. Okay, so we kind of draw it like this, but this is still a weird way to look at it and it's hard to rotate it. So actually we draw it like this. And this is actually a much easier way, even though it doesn't feel intuitive to you right now. This is a much easier way to draw this. So it just looks like this. I also have this theory that organic chemists are really lazy, so we make things as absolutely simple as possible. Any vertical line indicates a dash away, and any side-to-side line indicates a wedge towards you. So this is CH3, HH, CH3, fluorine, fluorine. So that's a lot easier to see, and these are actually much easier to manipulate as well, because you can, you can rotate molecules, right? So you can rotate this Fisher projection as well. And it would still be the same molecule. You have to rotate all 3. But I could rotate that Fisher projection So this fluorine comes down here. This hydrogen, oh wait, this hydrogen moved. This fluorine came down here. This CH3 came over here, and this hydrogen moved here. So you can actually see that here, CH3 hydrogen fluorine, and we rotated it to make the, let's see, what do we rotate? We made that iodine go back, the hydrogen's on this side, the CH3 is here. This is still the same molecule. So if this was the original thing that you had it in, it'd be pretty easy to manipulate it and get it to see the plane of symmetry. The other thing that these are really useful for is if your hydrogen is already pointing back, so this is a different molecule, it only has one chiral center. If your hydrogen is already pointing back, then you can just cover that up and do your priority, and 1, 2, 3 is going right at the top, so that's R. And just to remind you, that would look sort of like this if it was actually drawn out with wedges and dashes. Fluorine and CH3. So if you have a single molecule, you're looking at it from this angle, where two are coming towards you, two are going away from you, if that makes sense. But we just draw it as a cross. But if your hydrogen is coming towards you, you can still just assign the priorities R and then flip it and it's S. So either way works. Or you can physically break bonds and change it. That also works too. So what's convenient about these is they're easy to rotate and they're easy to assign RNS configuration to, and you don't have to do a lot of 3D visualizing of the molecule. So I tend to use these when I have diastereomers, or when I have two chiral centers, to check for what's a diastereomer and what's not. Because it's really easy to decide that you're just going to choose a molecule and line it up. So say we have, I like to use a model to help me not screw things up. Okay, is there a plane of symmetry in this molecule? I don't think there is, because these hydrogens are already lined up, but if you reflected the hydrogens across each other, then you get a fluorine and a CH3 not reflecting each other. So that's pretty easy to visualize. Now, if I took the mirror image of that, that's also easy to draw. So now I've drawn the enantiomer of this molecule. I don't know why I made that line so long. I have bad handwriting, okay? So let's assign RNS configuration real quick. Actually, no, you assign RNS configuration real quick. I want you to tell me what these are, and I'll give you a hint because there's not a plane of symmetry. It cannot be RS or SR. One of them will be RR and one of them will be SS. So y'all do that on your own. Ignore what I draw up here. I'm doing something else now. What's nice about these kinds of molecules is that the priority is always the same. Fluorine's always the highest, hydrogen's always the lowest. So you only have to figure out the highest priorities, lowest priorities one time. Oh, it's already 12:10. Okay, we're gonna solve it together so that you can have more time doing your recitation. How does that happen? Okay, so fluorine, or which one's the highest priority? Fluorine. And what's the lowest priority? And then between these two, they both have carbon. So how did you pick? That's right. So the fluorine beats this other one out. So this is 2 and this is 3. So let's ignore that hydrogen. So that's S configuration. Now let's look at that hydrogen. Is that pointing towards us or away from us? That hydrogen's pointing towards us. We want it to be pointing away from us. So the right answer is R on this one. So this is probably also going to be R because we know SR would be the meso compound of this. Okay, so now I don't have to reassign my priorities. 1, 2, 3, 1, 2, 3, that's S, but is this hydrogen pointing towards us or away from us? Towards us, so that's actually R. So I could go through the whole hassle here of then doing the same thing. 1, 2, 3. This is R, but there's a hydrogen pointing towards us, so it's S. Or I could know that this is the mirror image. So if that's R, this must be S. So that can help you kind of go through these practice problems a little bit faster. Okay, now, what do you think the relationship is between these two just by looking at them? Somebody said identical. Why? Do you have a good reason or did you just guess? That's what I would ask next. Nice. Yes. Yes. That's exactly what I would do. So there is a plane of symmetry here through this one. So you always have to check for meso compound. Now you could check for meso compound by, you're like, this one is definitely going to be reflecting of itself. One's R, one's S, whatever. So you could assign this and see if it's SS or RR. If you did that, you would know that the relationship between these are diastereomers or identical. Or you don't have to go through all that trouble and you can just rotate, which is what Lexi said, and redraw it because the top one's already identical, right? That one's already in the right configuration, but we just literally rotated the bottom carbon to change it without changing the stereocenter. And this CH3 would go here, this hydrogen would go here, and this fluorine would go here. And the way I drew that out, you might think like, oh, she's drawing it out for us and showing us exactly where each one moves to help us. No, I do this every time. I draw these little arrows so that I don't lose track of what's moving where every time, because that's where you get messed up. Because if you accidentally flip 2 instead of rotate all 3. So you got to rotate all 3. You got to know the difference between rotating an atom and changing the stereochemistry of an atom. If I just picked up 2 and changed them, that would change the stereochemistry of the central atom. Rotating all 3 doesn't change it. Okay, so what is the relationship between these? Identical. And what would you call this compound? Meso compound. That's right. What's the relationship between this one and this one? I heard some people say it. Diastereomers. So if this is RS or SR, it doesn't really matter because they're identical. Then something that's RR must be its diastereomer, right? So diastereomers, enantiomers, diastereomers, the same. Okay, you're gonna get practice on that today. Don't worry, and on your practice problems. Okay, rings can also be can be chiral as well. This ring on the left is, the ring on the right is not, because there's a plane of symmetry right through that middle there. So cis-trans rings, cis-trans disubstituted rings, if they're not exactly opposite of each other, whether you can just put a line right through the middle, plane of symmetry through the middle, usually are chiral. So this is a meso compound. The mirror image is the same. It's achiral, even though it has 2 chiral centers. This actually doesn't have any chiral centers. Does that surprise y'all? Why doesn't it surprise you? Yes, so this, normally though, you can have a plane of symmetry and still have two chiral centers. You do have a methyl and a hydrogen attached here. So a lot of times students will think this is a stereo center because there is a methyl, a hydrogen, and then two different carbon chains. But these are not two different carbon chains. If you follow this all the way around, like our rule, you would do CH2, CH2, those are the same. CH2, CH2, those are the same. You get to the middle at the same time, and they would both be a carbon attached to a carbon and another hydrogen. And then you kept going around the ring and it'd be CH2, CH2, and then you get back to the beginning. So there's actually not two different things attached there. It's actually two of the same group. It's just in a ring, so it's harder for students to visualize. So there's no chiral centers present. Even if there were chiral centers present, there's a plane of symmetry right through the middle, so you can tell quickly and easily that that is a not a chiral molecule. So both cis and trans of these are achiral. I don't recommend just memorizing this. That's one thing I don't like about these slides is I feel like they should throw these up there and they're like, so then you can recognize that when you see this, it's going to be achiral. Don't do that. Actually know how to find the plane of symmetry in the chiral center. Don't just memorize, oh, 1,4 cyclohexane, because inevitably something will come up that will mess with you and you won't get it right, or you won't be able to remember all that. Memorizing your way through ochem is boring and awful, so don't do it. Now, if we had 1,3-dimethyl cyclohexane, there's still this plane of symmetry when they're on the same side. This is an achiral molecule, but then this is a chiral center. Because if you go around the ring, the first ones are both CH2, those are the same. Let's go to the next one. This is CH with a carbon attached, and this is still just CH2. So these are chiral centers, but this is not a chiral molecule. Because it's a meso. Now, if you had the trans version of that, there is not a plane of symmetry because one's pointing up and one's pointing down. So if you cut that in the middle and reflected it, you'd get one down here and one up here. So no, not the same. So if they're trans, you want to make sure you're checking for the plane of symmetry. Always check for the plane of symmetry, visualize the molecule, and try to imagine if you can see a plane of symmetry. Because if you just memorize these things, I think it's going to be really hard. But if you can visualize the molecule, you'll always be able to get the right answer, whether your memorizing thing is working or not. So these are enantiomers. So again, this is like, oh, there's two chiral centers. There should be 4 possible stereoisomers, but these two are the same. So there's only 3 total stereoisomers. Okay. Oh, this is interesting. So enantiomers, they have the same physical properties because they have the same intermolecular forces at play. Enantiomers, not all diastereomers. We saw that cis-trans diastereomers don't have the same intermolecular forces. But enantiomers pretty much do, so they have the same melting point, the same boiling point. But when they interact with other chiral materials, then you can separate them. So if you are a chemist and you're working on making thalidomide and you're trying to separate out the good one from the bad one, they actually have like it's called a column that you run this material through, and one chiral molecule will come out faster than the other because the column is chiral itself too. So it starts to act weird and different when it interacts with other chiral molecules. The other time that chiral molecules act different is they rotate plane polarized light differently. So if I am able to somehow like filter the light so all the light waves are going up and down, like, oh, I don't know, maybe through your polarized sunglasses, all the lights are going up and down, and you shine that through a R or S, just one or the other, of a chiral molecule, they'll rotate in opposite directions. So if you're like, do I have the S or the R enantiomer here? I don't know. You can put it in an instrument that will shine polarized light, like what comes through your sunglasses, onto a chiral center, and it'll rotate one way or the other. Interesting. Some people want you to be able to calculate the degree it will rotate. I don't. But if you're going to have Dr. Dandekar or maybe another person, you should know that equation. But I don't believe in math and organic chemistry beyond percent yield. Yes.
Doesn't change is, what does it define the?
Ooh, it determines whether. So I'll draw this little dealie and because we're almost done here. Why do I keep doing that? This is what I want. So imagine, this is gonna be hard. I'm about to try to draw light. So imagine I passed light through some sunglasses. So light is like scattered all different ways. It goes like all kinds of directions, right? Light doesn't just go up and down. But then I have some sunglasses. And it passes through these polarized sunglasses. And you only have the up and down waves of light now. So all the waves of light are only going up and down. They're like only going vertical. So if I passed both of these lights, let's say I'll pass through a vial of like R, and then I'll pass through a vial of S, and they like actually have instruments that do this. The R will rotate it to the left. So I'm going to try to draw this, but literally I'm going from like up and down to this way. So it will rotate it that way. R doesn't necessarily go left or right, but we'll just say it rotates this way. The other one will rotate the opposite way. So if you're not sure if you have R or S of the same molecule, you can pass through a plain polarized light through the vial with that thing in it, and it will make the light rotate opposite directions. Yes. Oh, what a delightful question. If you have a mixture of R and S, if it's 50-50, that's what's called a racemic mixture. You need to know that. And it cancels out and it doesn't rotate either way. But if there's like 75-25, it'll be like slightly to one direction or the other. And so they actually do that to determine the ratio as well of two different things. Okay. So you do need to know that their physical properties are the same. Like a lot of times there'll be a question that's like, here's two enantiomers. What's true about these? And so your options are like, they have different boiling points. They react differently with this other molecule that's not chiral. So it would not do that. Or each enantiomer rotates plain polarized light in opposite directions. And then you're like, yeah, that one. You know, those are the kinds of questions you'll need to kind of know how they behave. But you don't, that's kind of the extent of it. Some people, there is a formula to calculate this, and some future professors might want you to do that, but I don't care if you do. And this is just kind of showing you like R and S have the same boiling point, same melting point, but then there's the rotation of light. So this is a picture of, oh, this is a better one. This is like the waves coming at you. Like light is actually kind of like this, you know, it's like going in all directions. And if it goes through a polarizing lens, it'll only go one way, and then when it passes through the enantiomer, it'll rotate to the left and the right. This is the equation that you don't need to know. So here's the plain polarized light. It's passing through R-butanol. It'll rotate to the left. Passing through S, it'll rotate to the right. I picked left and right arbitrarily. It doesn't necessarily go one way or the other. There's not like S is always left, R is always right. That's not true. There's not a consistent thing like that. And if it's 50-50, nothing happens, no net rotation. If it's only one, that's a racemic mixture, you need to know that word. If it's only one or the other, it's called enantiomerically pure. So we can check to see how pure it is. I don't think you need to worry about this too much, but I do want you to know that in some of the reactions that we are going to do starting in chapter 6 next week, you will be able to create chiral molecules. So that's part of why we're doing this also, is to lay the groundwork for you to know how the reaction you're doing is going to play out. Or you can make a mixture. Some of them will make mixtures. Okay. And that's called, if it can make one or the other stereoisomer, it's called stereoselective. If it's selective, it only makes cis or only makes trans, that's stereoselective. And then if it only makes one R or S, that's called enantioselective. Diastereoselective, obviously, same thing, it's more broad. Okay. This is interesting. Of the 475 billion in worldwide sales of formulated pharmaceutical products, what a terrible way to write that sentence. I need to edit it. 205 billion are single enantiomer drugs. So like if you are someone who does medicine, this directly applies to you. So here's just a few examples of those, and a fun thing for you to do is see if you can tell where the stereo centers are. Okay, and then this is Fisher projections, but we already did that. So the end. I'm sorry, I tried to get you more time, but at least you have what, 30 minutes-ish in your groups. So it's time for, you can take a break if you need to, come back, get with your group, and start doing practice problems. There's all kinds of practice problems here where you get to draw. I don't think I did a ton where there's 2 chiral centers because I wasn't 100% sure we'd get there when I made this, but do those on your homework because they will be on your exam. They will be on your exam. Very likely a free response question on your exam. Okay.